Go. Going live, and we're live. All right. Hello, everyone. If you're watching and you can hear me, let me know in the chat that, about half of these streams start with the audio just not working at all. So let me know in the chat if you can hear me, and if so, we will get started. My name's Joe Barnard. For those of you who don't know, I run a channel called bps.space. I'm sure almost all of you are aware of it, but we might have some folks who are not here. And today I am joined by Brian Douglas, who does a bunch of different things. He is maybe, depending on who you are, he might be well known for doing the control system lectures on YouTube. He also does a lot of the MATLAB Tech Talks. He's an actual real-life aerospace engineer, and we've got him on Skype today. So I'm going to hand it over to you, Brian. Here he is.
Hey. Yeah, hey. All right, yeah. Thanks for letting me sort of crash your Discord here and then kind of force this thing on you. I appreciate it. Also, I got a kick out of you calling me a real-life controls engineer because, I mean, you're clearly one also. And there's a lot on the based on the conversations on the Discord. There's a lot in your Discord as well. So this will be nice.
Yeah.
Just real quick, the reason why this came about was because your Discord is so active. Much more active than almost any of the other ones I've been a part of. And there's been a lot of really good questions about how you are going about designing your control systems for, the vehicles that you're building. And you and others are doing a really awesome job of answering those questions. And I try to chime in when I can. But I thought, why don't we just sort of go through a really high level overview of controls in a way that maybe won't answer almost anybody's questions because there's just going to be too many. You're not going to walk away from this and be able to design your own control system, for example, but you'll understand all of the nomenclature, hopefully, and all of the terms. And then you'll be in a better place to sort of ask questions about like how you, Joe, are approaching control design on your vehicles. And I don't know, we'll see. Hopefully this helps everybody.
Yeah.
So
I think it should be pretty fun. Yeah.
Yeah, let's share a screen here.
And just to make sure, everyone in the chat, let me know if everything looks good, if everything sounds all right. We went through a little test run yesterday to see if this works. So let me know how it looks here.
Yeah.
Okay. I'm gonna turn this camera off.
Okay. Well, you'll have to let me know, Joe, whether you see this or not.
Oh, I do. Yep.
Okay, good. I put this as an HTML because it tends to work better on streaming than doing it through Keynote. But there's a few little artifacts that happen when I generate an HTML, so we'll go from here. All right. So this is a presentation that I kind of changed really quickly yesterday for this conversation with you guys, and I wanted to sort of place in some information about Sprite as we go along, because I think that's what most people are interested in, so we can talk about control engineering and then kind of relate it back to what Joe's doing with Sprite here. And I stole some of his images and screenshotted some texts and all of that stuff, but I think most people on this already know what Sprite is. I'll give the briefest introduction, and then I'll throw it over to Joe to talk a little bit more. But it's a electric ducted fan, EDF powered, and you call it a hopper lander vehicle. And I think the idea behind it is that you wanted a platform that you could test guidance, nav, and control algorithms on a time scale that's a lot longer than the several seconds that you were doing with your model rocketry, right? And so this can do tens of seconds or minutes even, or longer if you wanted to. And so you're using this, you're building it all from scratch, writing all the software for it, designing all of the the hardware for it and everything, which is really impressive. And it's got a bunch of sensors on there and actuators, but the ones that I wanted to kind of highlight are things that you could potentially use in your GNC algorithms. Not that you're necessarily using all of these things, but you have a barometer for barometric pressure, an IMU, which is it's got an Excel and a gyro and a magnetometer on there, GPS, dual GPS actually, LiDAR, and then you have a gear on ground sensors, but I think you told me that you're not yet using that, but
Yeah, they're not
it's
installed yet. It's one of those things that when you design, I'll turn my camera back on. It's one of those things that when you design the vehicle, you're like, we could do all of these things, and then when you build it, at some point, you're like, this is going to be able to fly without these. We don't need them. So.
Yeah, yeah. And anything, yeah. You'll find a way to use it, I'm sure.
Yeah.
And then there's sort of two main actuators. There's the EDF itself, which is the main fan in the center that's producing most of the thrust. And then there's 4 thrust vanes, which is giving you control over the roll, pitch, and yaw torques. Mm-hmm. So I took this video from from something you sent out on Twitter, which I think is pretty awesome. Just kind of showing, so if people don't have a good indication of what this is, right? There's the big fan, the EDF in the center. It's generating this kind of column of air, which producing all of that force thrust, and then you are commanding these 4 thrust vanes in very specific ways in order to generate roll torques and pitch torques and yaw torques.
Yeah.
Is there anything you want to add to this before we move on?
The only thing would be the vane design is different now, but the concept is still the same. The two main actuators are just the fan, how fast are we spinning, how much force does it generate, and then the torques on the vehicle that can control all 3 axes, roll, pitch, and yaw, and that's just from those 4, vane directors at the bottom. So yeah, that's about it.
Okay, yeah, so going forward when we're talking about our control inputs, we're going to be talking specifically about these TVC vane positions.
Yeah.
I guess. All right. Okay. Let's move on here. So we're going to start at a really, really high level, and then hopefully we're going to hone in on something that's a little bit more specific. But, if you go to Wikipedia and you say, well, what's control engineering? It gives you this kind of control engineering is an engineering discipline that applies automatic control theory to design systems with desired behaviors in controlled environments, which is just a mess of a sentence. So the TLDR is that we're trying to get things to behave the way that we want them to behave. In most cases, we're talking about electromechanical systems. So these are things like Sprite, like your car that you're trying to design a control system for, or a spacecraft, or your phone, or whatever. It's some combination of electronics and mechanisms and things like that. But really, we can apply the theory that we learn for controlling those types of systems to any kind of system that's governed by dynamic equations. So dynamic systems like large-scale weather patterns, or even like you could adjust the interest rate to adjust the economy and inflation and stuff like that. Things that are just governed by these dynamic equations. And if you wanted to sort of really stretch this kind of analogy, you could talk about getting people to do what you want as a control problem. And and we'll get into that in just a second here. So the thing that all of those have in common, whether you're trying to control a dynamic system, electromechanical system, or people, is that there's these 3 questions that you're trying to ask throughout this process. And the first one is just trying to figure out what the current state is of your system. What's happening right now? What's the situation? What is Sprite doing? Is it hovering? Is it rolling? Is it tilted off to the side, right? Mm-hmm. Figuring that out. And then once you know that, you have to ask yourself, well, what do you want the state to be? What's the end goal, and what's a good outcome? Do I want Sprite to be in that state, or do I want it to be a little bit higher or a little bit straighter or something? And then the third question is, okay, I know where it's at and I know where I want it to be. What's necessary to accomplish that goal? How do I get to the end goal? How do I poke and prod the system in very specific ways to make the state what I want it to be? And so, like, if you talk about, quote unquote, controlling people, I suppose. Let's say you're in a discussion with somebody or in an argument with somebody, and you think, well, what do they believe? What do I want them to believe? And then how can I structure my arguments in a way that's going to change their mind? Right? So we can think about things like that in terms of as controls. This third question, by the way, is what I consider sort of the crux of the control problem, which is figuring out how to accomplish. Tend to think of autonomy as the very first thing, right? We want to get humans out of the loop. We want to build robots and drones and autonomous cars. And that's a perfectly legitimate reason to build a control system. But sometimes we do it to improve performance. like power steering assist on vehicles. That's not getting the human out of the loop. That's just improving their ability to steer the car. We may do it to improve safety, improve stability. Like some processes are inherently unstable, like nuclear power plants. And so in order to get anything of value out of them, we have to build a control system around it in order to make them useful. And sometimes we're just doing it to reject disturbances, like a 3-axis camera gimbal, for example. And these aren't all mutually exclusive. You know, they all are interrelated. But it's one of the reasons why almost everything that you interact with from a mechanical, electrical standpoint has some sort of control system involved in it. And it's usually one of these 5 reasons here. So we're going to step back now with now we sort of understand the goal of control, and go all the way back to the very beginning with an incomplete history lesson. And I also want to preface that I'm not a historian, so the history might be a little bit fuzzy here. Don't just take it with a grain of salt. The important thing is the story and the evolution of how we think about problems. So long time ago, the Greeks, specifically Ctesibius, developed what is regarded as the very first documented negative feedback controller. They were trying to figure out how to tell time with water clocks and be a little bit more accurate. And he came up with the float regulator, which is, what we have in all of our toilets now for the most part. And it's real simple concept is that if the water supply if the water level in the tank is too low, float goes down, water supply increases, raises it back up. And eventually you're going to get to some perfect water level where the amount of water being supplied into the tank matches the water leaving the tank. And you now have a steady flow rate out of the bottom, which you can use to act as a timer.
It's like a natural
regulator. The reason
regulator.
why I want to bring this up. Yeah. What's that?
It's like a natural regulator. It's pretty cool.
Yeah. It seems simple now, but it's definitely ingenious. And the thing that's important to note with this is that this is an example of model-free control. You might hear model-based control or model-based design and model-free control. And people have different definitions of what this means. For me, and what I'm going to talk about in this presentation, model-free means that you aren't building a mathematical representation of your system and then using that mathematical representation to help you in the design of how you want to change it, okay? So he didn't write a whole bunch of equations and come up with, fancy dynamics and come up with the answer that way. He used ingenuity and trial and error and heuristics and experience and stuff to design this. And people did that for a long time, and we still do that today. There's a lot of examples of model-free control, which is a lot better than model-based. Like for me, in the satellite industry, we do a lot of thermal testing and thermal vacuum chamber testing. And the thermal chambers are typically governed by like a PID controller to dial in the temperature that you want. And how that chamber reacts depends on the load that you put into that chamber. And so every time you change the load, you put something smaller in there or bigger in there or whatever. You're not going to go and redo all of your calculations and model that whole thing and then say the PI and D gains need to be this, right? You're just going to use your experience with using this device to tune that controller. So that's an example of model-free control. We have a choice. Ctesibius didn't have a choice, not because he wasn't, was lazy or something. It's just the math hadn't been invented yet. So we jump forward a number of years, and mathematics and calculus start taking off with Newton and Leibniz. They independently develop calculus, and then a whole bunch of people, including them, come along, like D'Alembert and Euler and Bernoulli and Lagrange and Fourier and a whole bunch of others, and they start applying these differential equations that calculus gives us to dynamic systems. So they start applying these equations to help us predict how dynamic systems are going to change over time. And they loosely take the form of this equation of, x dot equals f of x. And the way that we can interpret this is that if we have the current state of the system, which is x, and that could be, it's a vector of like position and velocity and roll angle and temperature and voltage, and anything that helps you describe the state of the system goes into this into what we call like the state vector. So if we have the current state, and then this is a big one here, and we know the structure and the parameters that connect all those states together, that function, we know how to connect them all together, then we can predict how the state's going to change over time. This x dot is the first derivative of x with respect to time. So it's how is that state changing is a function of the state itself. And that's sort of the baseline of dynamics right there. But that would only be so good. We don't want to just wind up, a spring system and let it go and walk away and just say, how's this thing going to react? Which is all x dot equals f of x allows us to do. We also want to be able to add what I'm calling intentional external inputs into the system. We want to change the state of the system by adding energy into very specific points in the system, which we'll call U from now on. And unfortunately, U aren't the only external inputs that get into your system. There's also unintentional external inputs that we'll call disturbances. So for Sprite, that would be wind gusts and temperature variations and all of the things that move the system that you haven't intentionally added in yourself. Like you haven't adjusted the EDF fan or the thrust vanes.
Yeah.
So the question is, what tools do we have to figure out what U needs to be? And we'll get to that in just a second, because the other thing, I added this in because there was a few questions on the Discord. So this is kind of a rough chart. Mm-hmm. But what I wanted to show you here is that, x dot equals f of x ud is like an abstracted version of what this model means. It's just some random function of x, u, and d. But there's a lot of different ways that we can represent that function. And the method that we choose depends on, the system that we're trying to model and what we're trying to do with it. For example, we could just leave it as a differential equation, time domain differential equation. That's a model of our system. If it's a linear system, we can break that high order differential equation up into a set of first order differential equations, which is state space representation. Mm-hmm. And sort of the so-called A, B, C, and D matrices. These are just a different way to represent the dynamics of our system. If it's a linear system and it's a single input, single output model, we could represent it as a transfer function. Same idea. We have some output, which is position, input is force, and we can write a transfer function that captures the dynamics of the system. If we wanted to be really fancy about it, or if the dynamics are too difficult for us to write out directly, we may represent our system with a neural network and then use some form of machine learning to figure out what all the parameters need to be so that the input-output relationship matches real life. So force goes in, position, and velocity come out. And then we have a number of hybrid model formats. If our system is discrete and the transition from one discrete point to another is governed by probability, we might choose a Markov decision process to describe our system. Or a state machine, like for you with Sprite, you may have a model that governs how it behaves when it's on the ground, and then switch to a takeoff state, mm-hmm. and then switch to a hover state, and then switch to a land state or something, right?
Yeah.
So all of that can be built into a model. So the thing here is when we're talking about a model, we're not talking about state space or transfer function or hybrid. We're talking about all of this stuff. We're just talking about a mathematical representation of the system.
I'll also, I just want to add real quick, all these, especially if you don't have a background in it, all these, equations and these fancy italic letters can look a little scary, especially if you don't have a background in it. But it's just, all of it is just an attempt at mathematically representing what's going on. The neural network is, funnily enough, I feel like kind of a friendly intro of it. It's just you're just trying to describe how the system works. And so there's a bunch of different ways that you can take to do that. There's seriously no one approach. Anyway, that's it.
Yeah, actually, you're going to keep talking here because what I wanted to show here is you shared this with some folks. is that you have chosen to model Sprite with state space equations and state space representation. So I was kind of hoping, if you wanted to, just talk about this chart, why you chose state space and what all of this means.
Yeah, sure. I'm going to move my camera up to the top right so that it's a little easier to see what's going on. Yeah, so at first this looks really scary. It's these two big matrices, and I'm almost certainly going to mess a few things up here. So Brian, just step in and correct me if I'm wrong on anything. But essentially, what I'm trying to model with these two matrices is, it's kind of like bringing all of the forces that come into the system, bringing them through each time step. That's what these matrices try to represent. And you'll notice that they're mostly zeros. They're actually pretty simple. So I'm trying to model Sprite as a rigid body, something that doesn't flex or bend or anything like that. So it turns out to be pretty simple to just carry forward these states. So on the left-hand side, look at the on your bottom left of the screen, you've got X, and then I'm labeling every part of what Brian referred to as the state vector. That's sort of a measurement of all the states that I want to track to describe where my system is, and it's really a measurement of all the states that I want to control on Sprite. So we have the X angle, the Y angle, the Z angle. Those are the orientations, the roll, pitch, yaw. Not in that order, but then we've got the angular rates. So those are the gyroscopes. That would be a direct measurement from the gyroscopes. We've got the position in real space and the velocity. So these are, where is the craft on my driveway or wherever? And then how fast is it moving away or towards that point? And then on the right here those are the states. And then on the right, U represents our inputs, just like that equation that we saw earlier. U represents the inputs into the system. So one of the inputs, these are the things that we talked about at the beginning as the GNC actuators. We have the fan force, that's in newtons. So how hard is the fan running to move the craft up or down? We have the TVC torque on the X, Y, and Z axis. So that's yaw, pitch, and roll. And again, you can label yaw, pitch, and roll in X, Y, Z however you want. But the point is that we can control all three axes. And so what I've done in the B matrix is define how do I okay, let's take a look at the top left of the screen where you can see X dot equals AX plus BU. Brian actually pointed out that the notation here is a little bit it's a little confusing. But the way that most state space equations, at least at a high level, you'll see them described or introduced is it's all by this one function, X dot, which is the change in the state vector, which is X. X dot equals AX, A times the X vector, times the state vector, plus B times the input vector. So the input vector is our U, the state vector is our X. And so these two matrices, at least, they are a total approximation. They're not considering the wind, they're not considering a bunch of things, but they are a pretty good approximation of the dynamics of Sprite. So when we have a TVC torque on the X-axis, it comes through this vector, and I described that the torque gets multiplied by the inertia divided by the inertia on the X-axis. And then it goes through based on where the ones are and a few other things in this matrix on the left. It goes through that matrix, and through that we sort of describe how any TVC torque on the X-axis affects all of these states. It doesn't for some of them, but it does for some others. So hopefully that is what you were looking for there, Brian.
Sure, yeah. Really anything, honestly. Yeah, so I'll just reiterate, with X dot equals AX, that's the dynamics part. Remember I said X dot is a function of X? The function is this matrix A that connects all of these things together, which is why the A matrix is called the dynamics matrix. And then it's a function of, X dot is a function of X plus U and disturbances. And here you're not modeling any disturbances, you just have U, and the way you're bringing U into the equation is with this matrix B. So it gives you a way to model how Sprite is going to move if you stopped the fan and all of the torques, how is it going to fall out of the sky?
Mm-hmm.
That's what A is going to tell you. And then when you adjust your inputs, B is going to tell you how those impact the state. And these are the 12 states that you have decided to model for your system. Even though there's an infinite number of states on the system, these are the 12 that make the most sense and are going to serve the purpose. So I think that's good enough, hopefully.
Yeah, because like in theory, we could try to model the actual fan speed. We could try to model the RPM. We could try to model the temperature on the craft, or we could choose to say, I actually don't care about the rate states or the anything like that. We could take states out of this and make it a little bit more simple. But I just chose this based on what I felt like would be a good number of states to control the craft, and through what a couple other people said they've used for different types of quadcopters. So that's the thing that has helped me a lot in designing Sprite, has been how close it really is to a drone or a UAV. And so I actually got a lot of the idea for how to build these matrices from a couple different papers that I found that went through how they had written out the state space matrices for their quadcopters. So there's a decent amount of resources online that you can sort of derive these from without having to write every single thing from the ground up and think it through. Or you can just use those as a jumping off point.
All right. So here's what's awesome, is that Joe is in a much better position than Ctesibius was. And that's because he has a model now of his system, right? And control theory provides tools necessary to analyze dynamic systems and then determine what the right inputs need to be. So that's what control theory gives us. And it sort of deviated from mathematics in the mid-1800s with James Clerk Maxwell. He was trying to describe this instability in these flyball governors and decided that the existing mathematics wasn't good enough. So, sort of developed some additional tools and techniques, wrote it down, and then boom, control theory has its own field. It began, and then it's flourished ever since. And what's awesome is that once you have a mathematical model of your system and you have a little bit of grasp of control theory, you can now approach your system with model-based control rather than model-free control. So it gives you a lot more options that you didn't have before. So there's a diagram that we're going to sort of build up over time here, and hopefully this will all make sense. But just to describe all of control engineering here is that we have some dynamic system, and there's two inputs, U and D, and there's the output, which is the states. And just to, again, bring this back to Sprite, U, in this case, we're going to talk about thrust vanes, because I'm always just going to talk about roll and not complicate things too much. Thrust vane commands go into this system. Sprite gets affected in some way, and then roll angle and roll rate changes, as well as other things. But we're gonna look at the roll. And then it turns out that the disturbance, right, other things are causing the vehicle to roll. There's environmental influences, and then there's internal influences also, like the EDF itself produces a torque, and that torque changes the state of the system. And now you're going to have to change the thrust vanes to handle that if you want to keep the roll angle constant, right? All right. So the question is, where do we go from here? It's a good question. All right. So here's where we're at so far. We don't know what the system is. Joe doesn't understand what he's working with just yet. He needs to describe it mathematically. He needs to build those state space equations. Or if you don't want to do that, you still need to understand at some level how the inputs affect the system state. And you need to know what disturbances are going to act on your system and what is the operating environment. You have to kind of understand all of this stuff before you can even really begin. Then the question is, what should the output be? And this kind of seems a little bit silly, but it's not as straightforward as you might think, right? You might say, well, I just don't want the vehicle to roll. But should it avoid obstacles in the process? Are you trying to minimize some kind of cost, like how much effort it takes you to hold roll constant? What is the actual behavior that you're looking for? So there's questions around there.
Just to give a quick example of this too, for the cost thing, there's a very real example of the cost thing, especially regarding rockets. There are a lot of actual launch vehicles that use open loop hydraulic systems to control their actuators, which means there's a finite amount I think this is now less popular than it used to be, but in some systems you have a finite amount of, control inputs that you can make before you just run out. Or maybe I really want to minimize, for that cost, I really want to minimize how much energy my servos are pulling from that battery. Yeah, Robert Cook just put it in the chat. Delta II has an open loop hydraulic control system. There's a bunch of rockets that's actually failed because of that. But that can be really important depending on how your system is designed, the cost of your actuators. Anyway, just wanted to interject.
Yeah, great. And then there's what I was referring to earlier, which is the main question, which is how do we get this system to generate the output we want? And there's two ways that we can do that. We have control over the inputs, right? Joe can move the thrust vanes, Joe can move the EDF throttle, but we also have control over the system dynamics. You don't always have to solve your problem with a control system. Sometimes your problem needs to be solved by going in there and actually physically changing the system. And that's a perfectly acceptable way of getting it to behave the way that you want it to behave. All right. So we have a whole bunch of tools and they go by different names. When we're talking about what is the system, you might look into system identification, which is building a model of your system using data. Or you might talk about modeling, like first principles modeling, where you're building a model of your system by understanding the physics and writing out the physical equations, directly. Or you might do analysis on a model or on the system to see what you've got. So these are the types of names that we refer to when we're looking up how to answer this question, what is the system? And then what should the output be is the planning problem. And then how do we get that output is both the control problem, which is figuring out what U is, and the design problem, which is maybe even changing the dynamic system completely at the mechanical level or the physical level, because that's the only way for us to get the behavior that we want. All right, so the first question we might ask ourselves is, well, can we determine U without knowing X? This is what's referred to as feed forward. So in other words, I don't know, can you see my mouse, by the way?
Yeah, it's actually really helpful.
Okay, good. So in other words, this, which I'm calling reference, what you might hear as like a set point or the command, is the thing that you want the system to do. So can you develop a system where, based on what you want it to do, build some function that's just a function of the set point, move the actuators to the correct positions, and then get the system state output that you're looking for without even knowing the system state whatsoever? So can we build this function, g of r, so that x of t equals our set point? And the answer is yes, we absolutely can. If the system has predictable behavior, it's robust to disturbances, and has relatively relaxed requirements. And the kind of sort of classic example, I guess, is the dishwasher. Is an open loop control system, right? The end goal, the system state that we're looking for is clean dishes, but we don't have any kind of monitors inside the dishwasher that's monitoring for how clean the dish is and then stopping it whenever it's perfectly clean. At least mine doesn't. I'm sure there are some out there that do that. What I do is I just set a runtime and let it go. And if the dishes are cleaned halfway through, not a big deal. Has relaxed requirements. If they're dirty when it's done, not a big deal. I'll just send them through again. And no matter how dirty these dishes are, how disturbed they are, it's still going to run perfectly fine, right? So this is a good example of why you would use feed-forward control versus building some sort of fancy feedback controller. To bring it back to Sprite, Joe, you have at least one feed-forward controller that I know of. I don't really know your system all that well. I just lurk on Twitter and Discord and figure out all this stuff. But I'm going to do a really poor job of explaining this, and then I'll throw it over to you to discuss more.
Cool.
So let's say we're talking about roll control, and we're trying to maintain a fixed roll angle, which means a roll rate of 0. And the way that we can command that is by moving those 4 thrust vanes. But here's the thing. We're lowering in altitude or we're increasing in altitude, and so the throttle of the EDF is being adjusted. Or even at any particular fixed speed, because it's moving air around, that's causing a roll torque to get into the system and move Sprite, starting to roll, which is not ideal. So here's something that Joe could do. He could ask himself this question. or not a question, just a statement. When the EDF throttle changes, I'm going to compensate for that torque by moving the thrust vanes a predetermined amount. I'm going to be smart about this, and I'm going to calculate exactly how much I need to move the thrust vanes whenever at a fixed EDF RPM, or whenever I accelerate or decelerate the EDF. And so if I predict this ahead of time correctly, while the EDF is spinning up, I could be real time moving the thrust vanes such that the output means that the system doesn't roll at all. It's perfectly compensated for. And that way, you don't actually have to know whether that's true or not. You don't have to measure roll because you've done all of your research and you were really smart about it and you figured out what this feed-forward controller should be. So I believe, Joe, that you are doing some form of this. Is that a true statement?
I will drop in and say that yes, it is, and it's actually one of the. So there are a bunch of benefits to this. I've actually seen, Ryan, you have a couple of videos where you talk about the benefits of adding, feed forward control where you can to just try and. The thing about it is, I could leave all of this to a feedback controller. And the way that would look is if I didn't have anything that predicted what type of thrust vane deflection we needed for any given roll angle, or for any given, EDF torque. When I spin up the fan, that the craft is going to rotate, Sprite is going to rotate because of that, because of the EDF torque. And if I don't have a feed forward in there, but I still have a regular feedback controller, eventually it is going to roll back to the correct angle because of the feedback. We haven't addressed fully the feedback stuff, but basically I would measure the roll angle and then change the vane direction because of that. But doing that puts stress on the rest of the control system, which also has to control a bunch of other things: roll, pitch, yaw, orientation, all of this stuff that it has to control. So I can just make everything a lot more simple by taking a really good, educated, sort of pre-measured guess at when I spin up the fan 10%, I know I'm going to need 10 degrees more momentary deflection on those, or even just a percentage, of the torque that I command from the EDF. So the advantages of a feed forward controller are that it's faster, and it also just makes, I think, the rest of your control system a little bit more predictable because you're introducing less errors for the feedback to try and correct for. And the feedback is still going to take care of some. Every time I spin up or spin down that fan, I'm not going to get it exactly right with that feed forward controller, but I'm going to get it really closely dialed in so that, the 3 to 5 degrees that I'm off can be easily corrected with almost no effort from the feedback controller. There's another good example of this too. There's a small version of, I say a version, but it happened before Sprite. There's a person by the name of, oh no, I can't remember his name. He goes by Tesla 500 on YouTube, and he built it's a really popular video. It's a electric ducted fan powered TVC rocket, a lot like Sprite, but it's much smaller. Looks like the whole thing is probably about this size, and it has real problems with the gyroscopic precession, rotating the craft around because of that spinning fan. So he has a feed forward controller in there. He knows that whenever he commands one, pitch on one axis, he's always going to need to provide just a little bit of correction on the other axis. And so instead of waiting for his controller to pick that up, for his feedback to pick that up, he just always commands a little 90 degrees offset deflection on those vanes. So hopefully this makes sense, but the advantages of feed forward are pretty great here, especially for the roll. That's probably the easiest way to think about it. When you spin that fan, you're going to need some counter torque, and you can just do that before you even measure any error.
Yeah, great. I think that every single time I finish a slide. Hopefully this all makes sense. All right, moving on.
Yeah, and if it doesn't...
We'll see what everybody thinks in the question and answer period here later. But
it also, if it doesn't make sense, just let us know.
Yeah. So feed forward is an approach to control. It's a perfectly valid approach. It gets used all the time. And like Joe said, sometimes it gets used in conjunction with feedback. So the reason why feedback control is here, negative feedback control, is that it's just too hard to predict everything, right? Disturbances especially, stochastic noise, and just all sorts of uncertainty in our system. So prediction goes out the window for really complex systems. So we use feedback, and feedback just basically means that the actuator commands, this U of T, the thrust vane commands, in some way depend on the current state of the system. Whatever the state of the system is, that gets fed back into this controller now, which is just a function of both the set point, the reference, and the state in some way. And there's a ton of ways to do feedback, but they all come back to this one point, is that the input in some way depends on the output. The thing here is that this puts a lot more pressure on designing the controller, right? You can really screw up. You can screw up more, I feel like, with a feedback controller than you can with a feed-forward controller. And here's sort of the quick explanation of why that is the case. Remember our plant, which is, by the way, the name for the system that you're trying to control. You might call it a process. There's like small, nomenclature differences between plant and process and system, all that stuff. But for our purpose here, the plant is Sprite. So the original Sprite dynamics are x dot as a function of xud, right? And now we're claiming, this is one of those weird HTML artifacts. Anyway, now we're claiming that u of t is also a function of the reference and x. And so when we feed u of t back, and it comes back into the plant here, we're making new connections. We have new connections between the state of the system and how the system changes. Remember, x dot equals f of x is the dynamics. So here, by doing a feedback controller, we are artificially changing the dynamics of our system. And when you do that, you can affect important things like stability. And you have a lot more, you can change performance, and you can change the way that this thing fundamentally behaves. So that's why we have to put a little bit more care into developing a feedback controller than potentially a feed forward only. Mm-hmm. So the question is, how do we design this function, right? Joe, how did you design your controller? We'll get there in a second.
Yeah.
There's a million ways, right? And you talk to anybody and they're just like, oh, I did all of this stuff and it was super confusing. But hopefully we'll try to simplify this. When you're developing a controller, you have kind of two choices you need to make. You need to choose a structure for that controller, and then you need to choose the parameters to populate that structure with. And in some cases, we call choosing the parameters tuning, but not in all cases. One of the more popular structures is PID, right? It's proportional, integral, and derivative, and it acts on the system error. Oops. And the system error is the reference minus the current state. So that's the structure. And then when we want to choose the parameters, we're trying to choose the proportional or the integral or the derivative term. We have three terms there. We may do it heuristically with trial and error and guesses and experience. We may do it systematically with the model of our system, whatever it is. So that's one approach. Another approach could be full state feedback. Basically what this is, it says, Joe has 12 states in his system. Every single one of those states is going to get fed back, and every single one is going to get multiplied by its own gain, and then the whole thing is going to get summed together. So now instead of 3 parameters, you have 1 parameter for every single state, and Joe has 12, for example. And I thought I'll start with this explanation, but if you want to chime in at any time, Joe, Go for it. But a few days ago, I guess it was, you had that live stream of a hop test, and somebody asked in the chat whether there was a PID controller on there, and you said, no, I'm using full state feedback, but there's kind of a P and a D in there, and I think people got maybe a little bit confused because it's really hard to understand just by hand waving. So I put this in here to kind of explain it, is that we'll take X angle and X rate. These are 2 states in the system, in the model that Joe's using. And so X angle gets multiplied by this K1. And added to that is X rate multiplied by K4, because it's the 4th one there. And so angle and rate is the derivative of angle. And so in this way, he has a proportional with angle and a proportional with the derivative of angle built into this system. And he has the same thing with y and y rate, and z rate, and position and velocity and all that stuff. So this kind of, in this case, looks like a whole bunch of PD controllers all wrapped up into this one big matrix multiplication.
Yeah, so I have almost nothing to add there. You covered it all. It's basically, so you can kind of see how it is basically a bunch of PD controllers, even though, from a technical try to say everything the right way standpoint, it is technically just full state feedback with direct gains on every state. But because of how I chose the states, it sort of becomes, because each state, I guess if you wanted to call them 6 states, which would be XYZ angle, XYZ position, each state is actually represented by the state itself, which is the angle, and then its derivative. And you can kind of see it. I don't think we have anything in the in this presentation, but we'll gloss over this more. But in the cost function that I described to develop these gains, I put way more priority on the angle than the rate, and the rate is just there to help null out as we approach the angle from a far off point. But we'll get to that more. Also, Nathan has a question. There would have to be a row in the K matrix for each one of the elements of the input matrix, right? Yes, that's correct. So at least in this case, the K matrix is 12 by 4, 12 across and 4 down. I'm not sure what the standard is for listing rows and columns on matrix, but it's 12 across and 4 down. 12 across because we've got all 12 states here represented, and then 4 down because we have those 4 inputs, which were fan force and then TVC, X, Y, and Z torque separately. So that K matrix multiplies with each one of these states in the state vector and then comes out as our inputs. But we'll get into that a little bit later. For now, the point is that it is essentially a bunch of PD controllers, but also that's only because of how I structured the state vector. Okay.
That's only because of the states that you chose.
Yeah.
If there was like temperature in there, obviously that wouldn't be a PD controller. It would just be proportional on that one. But yeah, so once you decide a full state feedback structure, you have a whole bunch of different ways to tune those gains. You could do pole placement or LQR or any number of things that we'll not really get into, but we will kind of.
Yeah.
You could do like a nonlinear structure like bang bang, which is just on and off. Again, you could build your controller, since the controller is just a function, as a neural network, right? That takes in your set point and your state, and maybe some history of your state, and if it's images, maybe a convolutional neural network, all sorts of things you could do there. And then the output is the commands that you want to send to your actuators. And then the process of tuning a neural network would be like some sort of machine learning algorithm to kind of estimate what those weights and biases need to be. And there's a whole bunch more. I didn't list all of them here, but I just wanted to give you a feel for the fact that you choose a structure and then you figure out how to tune that. And structures and tuning mechanisms are different things. And usually when I give this talk, I'm trying to like make a case for model-based design because people are like, I don't want to build a model. So that's why this is here. Usually designing, well, especially like for full state feedback, you almost require a model in order to be able to do that one correctly. So we have to build a model of our system for some of these. I don't know if there's anything necessarily to say here, but if you saw this tweet from Joe last year, hopefully it makes a lot more sense. He says, Sprite simulation starting to work. Linear model has been built with state space representation. Check. The control gains were generated with a method called LQR, which is linear quadratic regulator, for full state feedback control. So he's doing full state feedback. He chose all of those gains with a method called LQR, and he's doing his modeling in state space representation form. And then he puts all of this stuff together and shows, with some, it looks like some noise probably has been added into the system. He says, hey, look, it's basically doing what I want it to do. So this is the fundamentals of model-based control design.
Just to interject on what this is here, the noise, so this is actually a nonlinear simulation. So this is not directly through those state space equations. This is basically a more complex simulation where I've injected a bunch of noise into the system that you can see there. That's not a smooth signal for everything, and then I just have commanded. I think this is it's a pitch command. That green line is the set point. I tell the vehicle go to 10 degrees, and then based on those LQR gains, that's the response that I would expect to see, is that blue line. And then the noise generated in there is just like a guess at like, all right, well, if, you'll find out if the system is only marginally stable by injecting a bunch of noise and seeing if it can handle that pretty well. And it can. Anyway, that's it.
Yeah, that's a great thing to recognize here, is that you designed LQR and your full state feedback control with this simplified linear state space representation. But once you have your controller, you tested it on a nonlinear, much more complete simulation to see how it does. Mm-hmm. So that's definitely worth it.
So in that complete simulation.
Moving on.
Oh, sorry.
Yeah.
In that complete simulation, if you want to go back just one more slide, you'll see the vehicle actually starts at different angles here. Right at the left side, it starts at different angles, and I'm kicking it at the beginning of the simulation to try and simulate, what if things are misaligned a little bit? What if I don't get the vanes exactly aligned? So that's the benefit of that nonlinear simulation, is you can really try and simulate very close to the real world how things are going to perform and verify that your much more simple state space equations and LQR gains or whatever you generate have worked well. Okay, sorry, we can move on now.
That's great. Okay, so thought about the controller, we thought about modeling the plant. The next question is, well, what should this be? What should we set the system to? Just a step command? Is that good enough? Well, we don't know. This where planning comes in. This is where you determine the path. You determine whether you need to rate limit things or avoid obstacles or do keep out zones and all of that kind of stuff, right? Mm-hmm. Again, this requires a good model, typically. And, Sprite's not immune to this. I took a screenshot here. This is a little bit blurry because it was super small on my screen. I blew it up here. This is from your ground station software where you're measuring altitude. And this sort of green line that's a little bit choppy is the actual or the estimated altitude on board. And the yellow line here, this orange line, is the set point or the reference that you're trying to follow. And so I wanted to highlight this because this required a plan. And that plan was Joe going, I wonder what I should do. I know, a series of step commands, right? And that's almost always how this stuff starts, is you're trying to determine how does the system behave to step commands. What's the step response? In some cases, what's the impulse response? Mm-hmm. Or what is the response to a sine wave? These are the building blocks of planning algorithms, and it's how you dial it in and get the behavior that you want, which is probably not this behavior.
No.
It's much better now. I've seen it since I've taken this screenshot. So then, I don't know when today was, but at some point, you said, hey, I got this update here. Primarily, I got path planning function done, which draws out divert and larger maneuvers. I wrote a little program that looks at the magnetometer and GPSs to get a compass heading at liftoff, which tells the craft how to use NED coordinates to guide itself in the right reference frame. So this is, how path planning sort of evolves, right? You're testing with these step responses, and then nobody wants their vehicle to just step up and down, right? You want it to do something. And a lot of what looks like autonomy and smarts in the system is not actually the controller. What looks like smarts is the ability of some higher level function to tell it what to do, and then the controller follows it. Mm-hmm. And so maybe, I don't know if you want to talk about this or you want to move on, I'll leave it up to you, but figuring out how to develop a path that you want Sprite to follow is a lot of work, and it's part of the overall sort of control design.
Yeah, I'd love to talk more about this too. So the path planning stuff is really important, and the more I've gotten into guidance and control systems and just control systems in general, I've realized how important this is. So when you build this, I don't know, I think we kind of glossed over it, but when you build that linear state space model, you're building it around a point. It's what you'll see referenced as linearizing around a point. So my model for Sprite is a representation of how Sprite behaves. It's a pretty good estimation of how Sprite behaves when it's completely upright with no disturbances. but that's not always, where the craft is going to be. And if I were to, this is a kind of crazy scenario, but if it were pitched over horizontal, obviously like very high in the air, so you had some time to actually control it. The control system that I've developed is not going to probably work that well when the model is totally horizontal. The fan force is no longer going to represent in a direct way the vertical acceleration of the craft because it's totally horizontal. So we've linearized around this point of being upright. And so let's see, how do I tie this all together? When you do the path planning thing, Brian, I don't know if you want to just walk back a couple of steps to where we showed that pitch command in the simulation. You'll already see, yeah, there it is. You'll already see in the pitch angle, that's the blue line right there, there's some overshoot. So I've commanded it to go to 10 degrees, but that's a pretty serious, kick to the vehicle. Obviously 10 degrees isn't that much, but there's some overshoot there. And that overshoot is going to grow. Like if I commanded it to go all the way over to 45 degrees, it's really going to overshoot that, and it might kick itself to be unstable through that. So using path planning and just it almost feels like training wheels, like giving your control system training wheels so that you can how it's going to perform within a really close measurement of those set points or those references. And so the path planning or developing a way to tell the craft how to acceptably move from one point to another or avoid an obstacle or something like that. As long as you can track that reference and as long as that reference isn't sort of out of agreement with how the system works. Does this make sense? I hope this makes sense. That's been pretty important. So I don't know if there's anything in the presentation here, but I did end up getting the path planning working. So instead of those steps, which jolt the vehicle and it gives it this big oscillation in altitude, anyone in the Discord will have seen the test I did yesterday, where it's just going up and down the whole time. A path planning routine is going to really gently guide it up so that it can easily track that reference. Anyway, that's my little path planning spiel.
All right. There's a question there, how long this stream will be. I don't know. I was anticipating that you and I were going to talk for about an hour and a half and then maybe 30, however many questions people have. I can stick around for a while there, but I suspect about 30 more minutes of us droning on and then
yeah.
and some questions. All right. So the problem here that we've found ourselves in with feedback control is that I've just made this like bold statement that we're feeding back the states of the system, right? But we never know the true state of the system. So we've introduced a new problem here. And that's the fact that the true state of the system gets measured, and that measurement has noise and other errors associated with it. And so what we're getting is the output. We're measuring very few, specific things, maybe not the state directly. Maybe it's something that we can infer the state from. Like we may not measure velocity, but if we're measuring position over time, we can infer velocity, for example. And that's noisy. So we have the output Y is what we're getting out of our system. And that has to go through some sort of state estimator. That state estimator could be as simple as send it straight through. That measurement is good enough. Or it may be send it through a low pass filter, knock off some of that high frequency noise. And it could be something even more complicated where it requires a good model, which is like an observer, like a Kalman filter. And I'll get into that in just a second. But the bottom line is what comes out of this state estimation block is an estimated state, which is this X hat. So we never quite know the true state of the system. We have to measure it, and then we have to kind of figure that out. And developing this state estimation is another part of the control problem. And again, another tweet from last year says it's a little jank, but with how accurate the LiDAR and barometric pressure reading is and GPS, when they're all Kalmaned together, I might blah, 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 blah. The rest of that's not terribly important. The thing I wanted to point out here is that Joe's doing state estimation, at least in this particular instance, with a Kalman filter. And he's blending together the measurements from the LiDAR and the barometer and the GPS. So this is maybe will help folks, maybe not. I don't know, maybe it'll just confuse you. But this is my 1-minute introduction to a Kalman filter. How do we know state? How do we know something as people, right? How do we know how fast we're driving? How do we know the voltage of something? How do we know what time it is? Is that we have these sensors that allow us to measure the state. So we have a speedometer or a voltmeter or a watch or something like that. But we're not totally clueless people, right? We don't have to continuously look at our speedometer to know how fast we're going, or continuously look at our watch to know what time it is. We have this ability to predict, right? We have a model in our head of the world, and we can use that to figure things out, right? So if I look at my watch and it says, for me, it's 2:01, I can say pretty confidently that it is now not 3 o'clock, even though I've stopped looking at my watch, right? So we have these two ways to determine state. We have a prediction and we have a measurement. When we're talking about the systems like Sprite, both of these systems are inherently flawed, right? Your measurement is noisy. Mm-hmm. Your measurement is flawed. Your prediction, that state space representation of your system, is flawed. But rather than relying on a measurement alone or our ability to predict alone, a Kalman filter combines those two things together to get a better representation of the overall system. So Joe can use a noisy LiDAR and a noisy barometer and a noisy GPS to measure state, and then he can combine that with an imperfect Sprite dynamics model and how he's commanding the U, how he's commanding the EDF and the thrust vanes. So these two things can go together, and what comes out is a better estimate of state. And that's essentially what a Kalman filter is doing, is it's just providing us a way to combine a noisy measurement and a noisy prediction. You're doing that.
Mm-hmm.
You're using something called TinyEKF, which, again, we talked about this yesterday. I'd never heard of. I looked it up. It seems pretty cool.
Yeah, TinyEKF is great. To be frank, I actually don't have the dynamics model in the software yet. It's just the LiDAR and barometer right now. But as things move forward, we can add more inputs to that filter to give it a better estimation of where things are. But yeah, that's generally how the Kalman filter works, at least for extended Kalman filters and the like.
Yeah. All right. So we've got our planning algorithm. We have our controller. We've developed a model of our plant. Now we have our state estimator. And the last step in this whole process, well, it's not the last step because you're doing this continuously. Mm-hmm. But the last step in this presentation is we have to, simulate it. And we have to analyze it. And we have to test it. And we have to know what we ended up with. When Joe wants to know whether Sprite's actually going to work or not. And again, not always, right? There's a lot of physical testing and stuff, but sometimes and often analysis and certainly simulation, and tests require a good model of our system, right? So modeling is prevalent throughout all of this stuff. And Joe's done a ton of modeling. Let's see if this is going to work. These are videos.
HTML thing.
They're not videoing. Anyway, doesn't matter. If you're following Joe, you know that he does a ton of physical tests, right? He's out there doing his roll control tests. We already showed this one. It's a little bit dark, but simulated test. You're tuning your controller and you're seeing how it behaves in these sort of high fidelity models. Mm-hmm. And then you're doing a lot of what I would consider model verification, where you are updating your model with values that you get from test. So here you said, I built the Sprite dynamic simulation in MATLAB. I took a gut feeling guess at roll pitch yaw moments of inertia, and I got these numbers, and then I measured them tonight in prep for the first hop, and I got slightly different numbers. A little bit different, but different. And so you probably went in there and updated your model, mm-hmm. and maybe retuned the controller, right? Over here, this is a video that, again, is not working, but it's the TVC vane deflection test, which is basically the bandwidth. It's a test of how much bandwidth you have with your actuators. How fast can you move these things? What frequency range can you respond to mm-hmm. with these particular actuators?
Yeah, and so it's just looking at, like, when I command a deflection, this is a really tiny thing, but it affects the model pretty. These things control a whole lot of states. So I want a really good measurement. I used a high-speed camera here, but I wanted a really good measurement of what's the time difference between what does the time difference and the actual response sort of curve look like between when I command an angle, let's say 10 degrees on the vane that's shown there. When I command that angle, it looks like I'm going to a higher degree there, but when I command an angle and when it actually hits that angle. And so that could be represented, frankly, in my simulation, it's really simply represented as just a delay. In terms of when I command that, it's about 20 milliseconds before it can actually hit that angle. But you could represent that as a transfer function or a couple other things. And so that type of test helps me update my model to see, like, at some point, let's say the delay was on the order of 200 milliseconds or a half a second, there's going to be a point at which the actuators are not going to respond fast enough if they're slow, if they're too slow, if they don't respond fast enough. I want to know that in the simulation, because the simulation will show me this craft won't be able to stabilize really well because the actuators are too sloppy. So that's what a lot of the model verification was about. Was, I mean, there's a lot of expensive stuff flying on here. Let's really make sure all of this is dialed in and that I have the most accurate measurements I can before I hit the red button.
Yeah, and this stage of the game is, at least in my experience, and I think most people on the experience that are dealing with this, is the longest portion, right? Mm-hmm. I mean, it took you no time whatsoever to generate full state feedback gains using LQR.
Yeah,
it's a push of a button, but then verifying that the model that you built those gains off of is correct, and verifying that the final system is going to work in the real environment is what takes the majority of the time.
And it's actually
going in there and updating the model.
It's not. To give a real world example, like, my model is not correct. I found in the last few days that my velocity control, the gains that feed back and get multiplied by the velocity of the craft, those haven't been correct and reliable. There's a couple of reasons for this, but that's another part of what it is just trying to build it up and test each individual system because the simulation wasn't correct in some way. Yeah.
All right. Yeah. Awesome. Maybe we'll.
Oh,
what?
Nice.
Well,
there you go.
These were such cool videos too. I really wanted them to go. All your videos are pretty awesome though. So
thanks.
All right. Okay, so with all that being said, we have 5 main families of theory that we need to learn if you want to do control engineering. End to end, like Joe's doing. Modeling and simulation. There's the whole planning side of things. You need to be able to estimate state. You clearly need to go through and build the controller and understand some control methods. And then when it's all said and done, you have to be able to do some kind of analysis, system analysis, right? So that's sort of the breadth of the umbrella that covers what I think covers control engineering. Now, I debated taking this slide out, but I decided not to. I'm just going to blitz through this. Is that you're going to hear a whole bunch of terms, and basically these terms refer to, in some way, something that we've just talked about, and it's part of the decision that you have to make when you're trying to decide how to approach solving your problem, and how to make these decisions is much too complicated to go into in this stream, but I wanted to at least show you some of these words, right? You have the option of developing your control system model free, or you could build a mathematical model, or you can do a combination of both. You can solve your problem in the frequency domain or the time domain. You may implement your system on a discrete digital computer, or maybe it's in continuous analog electronics, and you have to approach those two things differently. You may design your system using suboptimal techniques, which sounds terrible, but like PID is suboptimal, right?
Yeah.
Basically, you're not optimizing some cost function, or maybe you want to approach it from an optimal standpoint. If you can get away with it, you'll want a simple linear model and linear controller. If you can't, you might need to think about nonlinear controller, nonlinear modeling. And then these two things we didn't touch on at all, but remember I said a controller has two things. There's the structure and then the parameters, which is the tuning. And there's different approaches that allow you to adaptively change those parameters over time so that it sort of adapts to the changing environment. And you can also vary the structure itself. This is especially true kind of in like neural networks, right? The structure's baked into the network itself, and that kind of morphs and changes as well as the parameters. So these are just some of the things that we need, consider when you're approaching your system. So Joe, I'll leave this up to you here. I can blitz through this map of control. This is the last bit that I have here. If you think that's a good thing to do, or should we pause for a second and see if anybody has anything burning that they want to ask?
I would say let's go through it real quick. I think it's really fun to look at it all because there's a sort of nice message at the end about like how you don't need to learn all of these things. But yeah, before we go into this, just know you don't need to learn all of these things to do controls engineering. But let's take a look.
Yeah. And I saw you made this the thumbnail, which is pretty cool. And if you've spent some time looking at it, also know that this isn't complete. I just wanted to give people an idea of the types of things that fit into these buckets here. So in the center, right, there's the float regulator, which kind of kicked it off. We got feedback control and feed forward control, and then some of the more popular domains that you might be working in, continuous or discrete, and you get back and forth between those with various discrete to continuous transforms, and there's a bunch of them in there. You might work in the time domain or frequency domain. You get back and forth between those with Laplace or Fourier if here, an electrical engineer, I suppose. I always like to think in Laplace here. And then around the outside is the 5 families of things that we need to learn. So on the modeling and simulation side, sort of the interior of this is the way that we choose to represent our mathematical model. Transfer functions or linear state space or maybe nonlinear state space. And then all of the hybrid systems with, Markov decision processes and state machines and all of that kind of stuff. And there's a whole bunch of stuff in here, but this is, got to think about how you want to represent your mathematical model of your system. The outer portion of this is some things that go along with that mathematical representation. You may want to simulate it, which has a whole slew of problems, like what sample time and what integration method and how am I going to log all the data and all of that stuff that goes into simulation. How am I going to display it all? System ID, again, is a way to develop a model using data instead of using first principle physics. We may want to linearize our nonlinear models. And then there's this idea of minimum realization, which is answering the question, what should I model? And the answer is model the least amount of things you possibly can, but it's enough to be good, which is totally nebulous and hard to figure out. But the more extraneous stuff you put in your model, the harder it is to troubleshoot, the more things could go wrong, the slower it's going to run, and all of that stuff. So there's this idea of,
as an example, I could put the temperature change in the EDF or the internal resistance of the batteries, or all sorts of things that I don't really need to model in Sprite, and it would just take a lot of time and bog things down. But I know the primary things I need to model, and so I can just focus on those.
All right.
Yeah.
Up on the system analysis side of things, the interior here are the types of things that we're concerned with when we're approaching a control system. These are things like, how does it perform? Is it stable? Do I have enough margin in the design? Is it controllable or observable? This basically means, do I have the right actuators in the right place that I can control all of the states? And do I have the right sensors in the right place that I can measure everything? And then sometimes we give our systems fancy names like non-minimum phase or, transfer order type or order number or something like that. And mostly that's just to help us realize the type of system that we're dealing with. Non-minimum phase, I'm not going to get into it. Too much. I have a video on it if you want to watch it. Then the outer portion of this is the tools that we have to help us figure this stuff out. The Gang of Six, which is, actually I just made a video on this too, but it's the types of transfer functions we may look at to assess things like performance and stability. We may look, if it's a nonlinear system, we may look at Lyapunov stability. We like to break things up into block diagrams. We may look at Bode plots and Nichols charts and phase plane charts and all of these different charts. There's charts and charts and charts. And all of these things just help us figure out certain things about our system. On the planning side of things, the left is the building blocks, is what I talked about, right? We have impulse response, and we have step response, and we have assign input. And it's not necessarily that we're going to command the vehicle like that, but it helps us learn how the system is going to behave, so that when we actually build the path planning, we know it's going to behave the way that we want. And part of that is like developing a map of the landmarks of the environment that you're going to operate within, avoiding, constraints and obstacles, and maybe solving an optimal path through some obstacles. And then there's this idea of holonomic and non-holonomic and redundant, which is basically a comparison of how many controllable degrees of freedom, I don't know if I'm saying this right, you have versus how many degrees of freedom your system has. So like, for example, a car can go forwards and backwards, and it can move a steering wheel left and right, which is only like 2. But yet you can go forward and backwards, and you can turn the car all the way around, and you can go in every which way in every direction. That's kind of a system that you're going to develop a different plan for versus like a robotic arm that might have dozens of degrees of freedom, and you can pick up that object from several different actuator positions, right? So you got to figure out that plan also. Down on state estimation, you may do something as simple as just calibration. You may remove bias out of a sensor. You may rotate that sensor into a new coordinate frame. You may filter the sensor with a notch filter or a low pass filter or something to get rid of noise. You may blend that sensor with other sensors and models of your system to fuse them together to get a better estimate of state. And if the state that you're trying to estimate is not yours, but something else, that just becomes the tracking problem. State estimation for something remote and not myself. And then one of the more popular ones is just this idea of the observer, which we've got into already, which is kind of combining models of your system and measurements to get a better estimate overall. And like the Kalman filters and the extended Kalman filter, clearly the most popular one, but they're kind of the heart of sensor fusion also. So there's a lot of overlap here in all of these terms. And depending on how nonlinear your system is and how much compute processing power you have, you may upgrade your Kalman filter to a sigma point filter or a particle filter. So things to think about. All right, so now that gets us all the way over to the left half side with the control methods. And there's a few high-level things that I wanted to just kind of touch on, but keep in mind that every single time I look at this chart, I realize I've left something out or made some kind of mistake. So there's a few that I want to add already. But just as a reminder, what this whole left half side is doing for us is it's trying to figure out how to find this function, a function of the reference or the set point and the estimated state. That's supposed to be an X hat. The estimated state. That's what our controller is. That's what we're trying to do. So, whoops, linear, backwards. Oh, I guess that is the first one. I'm not going to spend too much time on this, but linear basically means that it behaves, it follows these two properties, homogeneity and superposition, this controller. And really the main takeaway here is that you're only allowed to use 6 mathematical operations. If you're going to design a system and it's going to be linear, like a linear controller, you can only multiply or divide the input, integrate or differentiate the input, or add and subtract inputs. You can't add constants, for example. That's no longer linear. So if you want to build a linear mapping or a linear controller, you get 6 operations, and you can combine these in any way you want, but pretty linearly. And so, if you can operate within that linear region, awesome. And the reason why we want to do that is if we combine a linear controller with a linear approximation of our system, a linear model, man, we have so many easy ways to solve this. I mean, that's like why linear algebra is a thing. We can solve linear systems of equations really, really well. So that's ideal. And some of the, some examples of this is PIDs linear, loop shaping, pole placement, anything really in the frequency domain is going to be a linear control system method. Full state feedback, which isn't on here, is linear. And then over its counterpart is nonlinear. Let's see if this is going to do it. Nonlinear, anything that's not linear. If you're using anything other than those 6, it's nonlinear, right? And typically, you're going to upgrade to a nonlinear controller when your linear controller just won't work. Your system is too nonlinear to be controlled by one linear controller. And a couple examples of these is like gain scheduling, which is probably one of the more intuitive nonlinear controllers out there. Gain scheduling basically says, hey, I bet you a linear controller is going to work over this really small range in the state envelope. Like as long as I'm just in that at this temperature, a linear controller is going to work. If I get out of that temperature, it's no longer going to work. But a new linear controller might work, and I can just switch between those two. And so what this is saying is build a whole bunch of linear controllers and then just switch between them, schedule them based on the situation.
If I can interject here, as just you can tell me if I'm wrong, but I think an example of this that might tie back to rocketry is if you're flying a liquid fueled rocket and your center of mass and your moment of inertia is always changing, you can schedule the gains to change as that changes. And so you know that a linear system is not going to represent, or a linear controller, just one, is not going to represent your control gains and how the vehicle can be controlled through the whole burn, the whole depletion of the fuel tank. But if you linearize around a bunch of, parts of this is how full the fuel is, and then this is how full, and then this is how full, if you linearize about those points, you can schedule those different gains and basically address the whole control problem by cutting it up into a bunch of different sections.
Yep. Yeah, exactly. Other examples like bang bang, which are off and on, and sliding mode, and backstepping. And I'm not going to get into these because I wanted to be done here hopefully by 2:30, so we have plenty of time to talk with folks. Here's the important part is every single controller falls into one of those two categories, linear or nonlinear. That is a pure dichotomy there. All of these other things we're going to go into are overlap. Okay, sometimes they're linear, sometimes they're not. It can be robust and adaptive and optimal, all of these things. So don't think of these as hard, fast descriptions. Just think of these as terms that you may apply to your system as you're developing it, right? Or at least understand what these terms mean. So like if somebody says robust control, this is the question they're trying to ask. Can a single static controller work even in the presence of model or disturbance uncertainty? So, for example, Joe's model is wrong, right? It's a linear model. It doesn't match reality. But if it's a robust controller, that means that it can handle some amount of variation, some amount of uncertainty between the model and the real system before everything just goes, to pot. So an example is like if you're building a bunch of drones and you want a single PID controller to just put up, like you're building toys, and you just want to put the exact same PID controller on every single one, but manufacturing defects and tolerances mean that they're all slightly different. You would want to make sure that your PID controller is robust to all of those variations. So that's the theory of robust control. And there's a bunch. There's H infinity, which is probably the most popular approach. There's like mu synthesis. There's this Lyapunov-based control. Loop shaping is actually a linear robust control method. So again, overlap everywhere. Adaptive control asks the question, well, why are we using a static controller when we can just build one that changes to the situation? And this gets back to what you were just talking about, Joe, with game scheduling. You could game schedule, or you could have an adaptive controller where the gains themselves are changing as the mass changes or the CG changes or something. And it's a form of state estimation because you're trying to like estimate the model as you go and then change the gains real time. Some adaptive control techniques are like extremum seeking or model reference adaptive. I'm not going to go into too much detail on all this stuff, or iterative learning control. You can look these up, but these are forms of adaptive control where it just says, hey, I want to change how the controller is responding real time as we go along. We could choose some form of optimal control, and optimal control, this is going to pop up. I think this is killing my computer, by the way.
Oh, yeah, I'm sure.
Yeah, it is not happy at the moment. Its fan has been going nonstop. This says, why are we tuning a controller manually when we could just optimize an objective function, right? An objective function says, if I can write this function that balances or combines performance and cost, can I just find the perfect set of gains that minimize this function when subjected to the dynamics, right? And that's what you're doing with LQR.
Yeah. Yeah, I set a
Just
cost. I said, this is how important it is that that you control this state, and then this is the cost of using the actuator. You combine those two through the function, and then it gives you this is the gain that's going to get you those results.
yeah, we may.
Uh oh, it's struggling.
Oh no.
Uh
Hey, there we go. Okay, LQR, right? It's a way of setting a quadratic cost function applied to a linear system so that you can find the proper regulator gains.
yeah.
LQR, linear quadratic regulator.
This web
Oh,
page is
now
choosing
Safari's not
significant.
happy.
We're almost there.
Wait, there's like two more here. Um, but I can hand wave the rest.
Let's see. Maybe command the next slide and then just start talking about it. See if it. Oh,
Yeah,
we might be.
I got an idea.
Okay.
This is going to be less than ideal,
It'll
but
be
we're so close.
Yeah.
We're just going to finish it.
Oh, you'll
this
just go.
way.
You'll just go from the image.
Oh man, this isn't going to work. Oh well, it's fine. All right. So now we're over here in this predictive control side of things, and predictive control just says, hey, if we have a model and we're able to predict the future, why don't we just run that model every time step and add some constraints into the system and build an objective function, and then just instead of optimizing once like you do with an LQR, why don't we optimize every single time step and rerun the model over and over and over again, making predictions into the future and figure out what the best command should be by running this model. And that's the basis behind model predictive control. And there's a lot of different flavors of that. There's robust MPC and linear MPC and explicit MPC and all of these different ways of running an optimizer and a model real time on your system to predict forward into the future.
Mm-hmm.
And then, then there's this idea of intelligent control. And intelligent says, hey, why don't we just let artificial intelligence solve our problem for us? Why are we mucking around with all of this knowledge? Let's just set it and forget it. And there's a ton of problems with it, but it's very compelling. And so basically, hey, why don't we just have this universal function approximator, this neural network, set it up, set my computer up to learn what those gains and weights should be, come back, and then it'll just be perfect. And some ways that we have to do that is with reinforcement learning or genetic algorithms or like fuzzy control, which is using like Bayesian probabilities and trying to figure out what that right function should be. So we've got that going for us. So this sort of answers the question right away here. But this is the thumbnail here, which is usually when I talk about this with folks, one of two things happens. They either panic because they think they need to know all of this stuff, or they are more impressed than they should be because they think I know all of this stuff. And a lot of this I don't really know very well at all, is the bottom line. And I haven't had to know it because in my particular field, it hasn't been terribly important for me to learn it. And so what I've done here is highlight, which you guys probably can barely see. Let's get rid of this. That you guys can barely see here. But these are the things that I've got a lot more experience with just in my day-to-day job of what I've done. It's heavy on modeling and simulation. It's heavy on state estimation. A little bit of planning, but I'm a space guy, and mapping, and we've gone to places where I haven't had to deal with a lot of this stuff. Mm-hmm. And a little bit on like stability and performance and things like that, but like no controllability, observability. I've never worked on a non-minimum phase system. And on the control side, I've really done everything with these four: PID, LQR, gain scheduling, and bang bang.
Just to go back,
had to.
Sorry to interrupt, but one thing that helped me a lot. We had a conversation a while ago, but one thing that helped me a lot was you explaining that at least for the controllability, observability, I was asking something about that a while ago, and you were like, "Yo, I've never seen anyone use that in the real world." There are so many of these things that over time you just develop an intuition for, that you're not always going to have to do every bit of math for it, or you're not always going to have to you know, run a bunch of calculations to understand, is this going to work or is this not?
Right. Yeah. I want to clarify though. It's not that it's not important, because some people do run those, and it is important to them. It's just the systems I've worked on, I've never had to determine whether it was controllable or observable, because it was intuitively obvious. Like, for example, with Sprite, you could remove 2 of those thrust vanes and just have 2 in line with each other. You can do the mathematics and then solve for the controllability, gram in, and then realize you can't control one axis.
Yeah.
You can absolutely do that, and it's going to come out and mathematically tell you that. But you have enough experience and intuition with your system to look at it and be like, wow, if I only have 2, I'm not going to be able to control that axis. Let me get 2 more. The nice thing about these controllability and observability, though, is it can give you a degree of controllability, too. Like, even though you may be able to control all axes, one of them is, like, really weak compared to the other one. So there is use there, but just the problems I've had to solve, they haven't been useful to me. And the case with a lot of this stuff also.
Yeah.
These last 2 doesn't really, I won't go through this. I just wanted to let people know control engineering is way more than just control theory, right? There's systems engineering and integration and test and writing software and buying hardware and product management and all that stuff. Everything that you're doing, Joe, right, is part of the whole process here, right? It's not just a bunch of theory. There's a lot of things that go into it. And then the last thing here is just sort of a plea as a control engineer, is that you don't always have to solve things with feedback control. You don't always have to be like, this thing's total crap, but the control guys can fix it, or the software guys can fix it, or whatever. So I put here, good control system design begins with a good system design. And we had a conversation yesterday about how your IMU is off center. And so now every time it rotates, pure rotation looks like an acceleration. Also, there's some component there in your IMU. You can absolutely fix that in software.
Yeah.
And I know yours is a little bit hard because you have a ducted fan right in your CG, so you can't really put the IMU there. But in a different system, it may be worthwhile relocating the IMU, for example, rather than trying to struggle and figure out how to solve this problem after the fact.
Yeah, I could spend a week and a half on the math and the implementation for it, or I could just, at the beginning of the design phase, if I had the option to, I could just be like, well, we could just make some room here, put it at the CG, and then essentially eliminate that problem down the line.
Yeah. So that's what I had here to go over. And I said an hour to an hour and a half. It was just about an hour and a half. I'm always on the long end. I tend to talk more than I probably should. But hopefully that was useful and helpful. And we'll do some questions here for sure. But there's a lot of good people that are on your Discord, and a lot of good people on the controls theory, I guess it's called, the channel. And I'm on there occasionally, but people ask questions, people get answers on that. So I would recommend that if you don't get your question answered here, or if you're just slightly confused about a topic, go to the Discord and post your question there, and somebody will have a good answer for you. But hopefully this allows you to frame your question a little bit better, or know some of the nomenclature to use.
Yeah. So let's do, thanks a bunch, Brian. This is awesome to have this presentation, especially in the light of Sprite. So it makes a little bit more sense for people who are familiar with the project, if you are. But thank you so much for putting this together. And I feel like, if anyone has questions or anything controls related that you thought, could we cover that again, or something was confusing, just drop it in the chat here. I'll open up the Discord too and see if I can get questions in there, but the YouTube chat is probably a little bit better. So I guess we'll go through them now. Christopher Silva says, I've used concepts like controllability/observability to convince supervisors that some things are impossible. That's one way to do it. Yeah.
You know what's funny about that statement is there are certain things that I've done just because that's the way that a supervisor likes to see it, or the only way that they can be convinced. And I don't want to put them down, because everybody's like that, right? Is it's like, if I only want to see
Nyquist plots, and I'm like, don't show me a Bodhi plot. I don't care. Show me Nyquist. And the person doesn't like looking at Nyquist plots. They're still going to do it because that's the way that I like to look at things. And so I totally get that sometimes you just have to do something because your supervisor, that's the way that they want to interpret the data. And it might just be like Christopher says, look, this is impossible. This says so right here.
But if you want to see the math, like here's the proof. Yeah.
Yeah.
Brian, I'll turn you over to this next one from Mad Hoyen. He says, in my linear systems class, they said we could get integral effect in full state feedback by adding a new state, which was the difference between the actual state and the reference state. How does that work?
Oh, I should probably have a good answer for this. I could probably reason through it.
Also, Brian, do you want to turn your camera back on too? Or,
yeah.
Switch off the screen capture.
Yeah. Let's get back to that. Let's see here. Sorry. Stop sharing.
There we go.
All right. We're back. Let me get the... Oh, okay. Yeah, so... Oh, this is... Oh, I'm in... Sorry, guys. This is a calamity of errors here. I'm in full screen mode.
No worries.
Okay. I don't know off the top of my head. I'd have to look that up and let you know. Usually the way that I add an integral effect, I guess, in full state feedback is with integral feedback. Like if you look up full state and integral feedback, you can difference, take a difference of the state or the reference in the state, and then you can send that through an integrator, and then that goes into your full state feedback gains. And you can look up something like LQI, which is linear quadratic plus integral or something like that. Mm-hmm. And that's typically how I've done it. This might make sense. I'm sure it makes sense. I just haven't thought about that by adding a new, like a difference state and getting an integral effect in that sense. I'm sure it works. I don't know. I don't want to give you a bad answer.
Nathan also said, Nathan actually has a great example. He's been cruising through the state space stuff in the Discord, but he asked, how is gravity implemented in the state space model? Is it just set as an initial acceleration in the state vector? The way I actually didn't include gravity in, never mind. No, I did. I included gravity in my state space model, but not directly in terms of the craft moving up and down. I included it only as a way to show velocity over time when the vehicle's pitched at an angle. But I think I'll turn that one over to you as well, Brian.
Yeah, so I'm gonna guess how you're doing something here. Is the problem with gravity is that it can make your system nonlinear, depending on how it's implemented. Like for example, when Sprite's sitting on the ground, a linear model would assume that a little bit of thrust and it's going to start to rise up. But that's clearly not the case. You need a lot of thrust to overcome gravity. Mm-hmm. And then a little bit of thrust more only gets you a little bit faster, and a little bit thrust less gets you less fast, right? So once you're off the ground and operating, you can operate in this sort of linear mode. So one way that you can do it is assume there is no gravity.
That's what I've done.
That the system in the state space equations, that the system is linear, and you can design your controller as though any slight increase in thrust is going to move you up and any slight decrease in thrust is going to move you down. What that does, though, is it puts the onus on your ability to cancel gravity later on so that truly is the right condition. So in order for your linear controller to work, you have to provide it the situation that you claimed it was going to be in. Which means you need to...
That's exactly what we were working through today in the Discord for determining the hover speed for the fan. Is if I don't have that speed set exactly there because I didn't account for gravity, the control laws that I have no longer work how I'd like, because I'm not actually, that gravity is entering the system and it's something that I haven't accounted for.
Yeah. So that's on the control side of things. In terms of just pure modeling, state space can absolutely handle gravity because that's an external input. it's a force or an acceleration that comes in through your B matrix. So you just take into account that that's a downward force, and you just throw that into your B matrix. So in terms of modeling, that's pretty straightforward. But in terms of like if you wanted to do LQR, I don't know if it's typically in that model. I have to think about that, but I feel like that's just going to make it a nonlinear system, and it wouldn't quite. I don't know. I'd have to think about that, but I think the way I would approach it anyway is not include it when I'm designing my controller, and then definitely have it in there for the real system that I need to take it out in some way. Feed forward can do that. Adaptive control can do that. An integral can do that. There's a lot of different ways to sort of take that out.
So Ramira 3D, who's Rodrigo in the Discord.
Okay. Hey.
Yeah.
Hey, Rodrigo.
He asked, in Sprite's case, what are the advantages of full state feedback control with state space versus PID? I'll address it a little bit, and then Brian, if you want to add anything on.
Go for it.
So I went with full state feedback after doing a lot of work with staged PID controllers, focusing on one state. So for Echo, which is the rocket that for a long time I tried to land, I had staged PID controllers, and what that looks like, I'll try to like hand wavy explain it. I had a PID controller that focused on zeroing out the error for the orientation of the vehicle. So that looks at the rate of change of the orientation and the actual orientation itself, right? But then, in addition to that, I wanted to control the velocity of the vehicle. And so I had a separate PID controller that goes sort of, I almost think of it like an upside down layer cake of like a second PID controller goes on top of the first. And so if that first one isn't tuned really well, if you don't have if you don't understand exactly what the response in that first controller is going to be, it can introduce things that you don't want in that second controller. And so if you wanted to control, let's say, the orientation and then the position, or the velocity and the position or something like that, you're stacking all of these controllers up. And I didn't have a very good model built up of the total, both the dynamics of the craft, and then the actuator dynamics, and a few other things. I didn't have a very good model built up for Echo, so I just was accepting a ton of error in my control system. And so the thing that really drew me to the full state feedback approach, A, was that it was something new to learn. I had never tried that before, and then B, I liked the idea that I could have. I could design the whole controller at once, so nothing was staged, nothing was. I mean, it does kind of build on top of each other. Everything builds on itself in that K matrix, but it all happens at once. So I give it the position, the velocity, the rate, the angle, and it just gives me those TVC angles that I want. Or really, it's the torques, but I liked the idea that I could give it all of the things that I wanted to control. And using the full state feedback and LQR, I could just get directly those outputs that I wanted instead of trying to connect all of these staged controllers together. Brian, if you want to add anything on, you're welcome to. But that's what drew me to it, at least.
Yeah, I think one of the benefits is that PID is a single input, single output controller. So you're going to have a bunch of them, one for every state. And I made a video that was a really high level. I don't know if it'd be interesting to anybody here. It's probably too high level, but on drone control. And there's a very similar problem with drone control, is that just like with a rocket, there's no actuator that can move a drone like a quadcopter, translate it, to the right or the left, for example. You have to rotate first and then go off to the right or the left. And same with a rocket or with Sprite, right? Sprite can't just move to the right or the left. Joe's got to roll it first and then move over and then roll it back, type of thing. So the same problem. So what you end up with is cascaded single input, single output controllers, where there's an outer loop that is determining the position that you want the vehicle to be in. And then from that position is commanding a roll and a pitch angle. That becomes your set point for your inner loop PID controllers that then try to match that And it just becomes pretty complicated because everything is interrelated on each other. So the more complicated it becomes, the harder it is for all of these cascaded PID controllers to get tuned, and it can become a bit of a mess. So with LQR and with full state feedback, you have the ability to tune everything all at the exact same time, rather than one loop at a time or anything like that.
Yeah. We got one more question in the chat here. I'll just remind everyone, if you have like any questions about control, we're both happy to chat about that stuff. So yeah, keep just putting stuff in the chat and we'll answer it. But the next one is Christopher Silva again. Could you talk about determining the initial state of a system for state estimation? This has been the hardest part of working with Kalman filters in my experience. I'll let you handle that, Brian.
Sure. Yeah. So I'm gonna guess that you're doing an extended Kalman filter, because a regular Kalman filter is linear, and it turns out that with a regular Kalman filter in a linear system, it doesn't really matter what your initial state estimation is; it will converge on the eventually. It may converge really, really slowly. The problem comes with an extended Kalman filter because you have a nonlinear model. And every single time that runs, it linearizes the model at the operating point and then uses that to predict forward, this linear model. And if you're way off on your guess, or it's like a really nonlinear system, you're going to maybe not ever converge, right? If you're really far away, because the linearized version of that model is nowhere near the real behavior, and you're just going to constantly like walk away from truth. You're never going to converge. So coming up with an initial state, it really depends, for me anyway, on what sensors you have available and how much time you have to sort of estimate a state externally to the Kalman filter before you turn it on and let it start running. Because with my experience, the sensors have been pretty good, right? They're good enough to know coarsely where something is or the state of something. It's just not good enough to get the performance that I really need out of my system. And so I can just, take a running average or a low pass filter or something of all of my sensor states and say, I'm approximately here. And that's been good enough to seed the initial state of my Kalman filter. And then I let the Kalman filter run in the background. I don't want to rely on the output until it's converged. And I let it run in the background until it's converged. And, the covariances have all converged and everything looks good. And then I switch over and start using that output. I'm making it sound a lot easier probably than it is in certain situations. Again, my projects I've worked on have had very nice sensors and very predictable systems. And so coming up with an initial state hasn't been terribly difficult to do. For me, I feel like the hardest part is either getting a good model of my system that I can actually run a Kalman filter with, or coming up with the process covariance noise has been potentially difficult. Anyway. So that's that. The questions are building up. Hopefully that answered something, but yeah, you really only have to worry terribly about the initial state for these nonlinear estimators, because they can not converge. All right.
So the next one here is, tell us more about tracking. If you have any specific things you'd like to know about, we can talk about those. I don't have anything specific to talk about with tracking other than it's a thing.
I have a series, a MATLAB Tech Talk that talks about sensor fusion and tracking. It's 5 parts. The last 2 parts are on tracking, and it's really interesting to me. I haven't done a lot of tracking, so I had to learn it for that video.
Oh, I think I watched this. I think I watched this setting up all my IKEA furniture like a couple months ago.
Oh, yeah.
Yeah, I went through them all. They're really good.
Yeah, so it basically, tracking is difficult because when you're trying to estimate your own state, you have access to you. You know how you're commanding your own vehicle, and you can use that to predict where it's going to be in the future. When you're tracking, you don't have access to that. So now you have a lot more uncertainty of where that vehicle is going to be, because you don't know whether the driver is going to move the wheel or step on the gas or anything. So you have to do some other fancier things to sort of account for that lack of information. So that's how tracking is so much harder than your own state estimations because you have less information to go off of.
Nuffly asks, unrelated question, but is Sprite Stream still happening today or not? Nuffly, I'm afraid not. I've got a couple of things I want to fix in the software first, and at a certain point, it draws away. I want to make sure Sprite is ready to hop before I stream about it. So that'll come probably in a few days. But and then Ramira said, so in Sprite's case with 12, oh my gosh, I can't speak. In Sprite's case with 12 states, you'd need 12 separate PID controllers all trying to work together. I can see how that would be really complex. Well, 12 certainly would be very complex, but because of the way I've structured the state vector, I would actually need 6 PID controllers to represent that. But still, six PID controllers coupled together is a lot of cascading, as Brian mentioned too. It's just you're coupling a lot of things together that if they're not all totally optimal, errors can propagate through the system in weird ways. And then the next one, Joe has been using MATLAB for simulation, and that's what we have been using in university. How widespread is open source software like Python for simulation and modeling? So I've seen a couple of my friends go the Python route, but Brian, you've worked in the industry. I mean, you've worked in the real industry, and so you probably have a much better experience than I do for answering that.
Yeah, it depends. Like when I was at Boeing had its own in-house Simulink-like software for a long time that we used, and then we ended up going with MATLAB to develop control systems and then build diagrams from those that we would ship off to somebody else to code it up. And then in some of the smaller programs, I've used MATLAB and then AutoCode. And others, we've used Python. It all depends on sort of how kind of scruffy you want to be. If you don't have a lot of money or people are already familiar with Python, Python is awesome for those purposes. The nice thing about MATLAB is that there's a lot of knowledge that people already have on how to use it just because they've used it in universities. And there's a lot of support, professional support, not just like, Stack Overflow or something, but a lot of professional support for people. And so it can tend to save companies a lot more money by using it versus something else. But like SpaceX, I've never worked for SpaceX, but
they're on National Instruments, I think.
Well, they do all of their modeling and control design in C and Python, I believe.
Oh, okay.
Like, I don't think they use any. Well, I don't know how much MATLAB they use, but I do know that if you don't know C or maybe Python, but definitely C, that you're have a hard time, I think, getting a job with them because so it depends.
Yeah.
Well, MATLAB's definitely widespread. Python's widespread. C is widespread.
Yeah. The next one here is, I've seen a lot of complex MATLAB models that were linearized with the MATLAB toolbox, and then robustness or sensitivity analysis was performed. What do you think about this approach? Brian?
Yeah. So, so robustness basically means how sensitive are you to variations in your system. And what I've found is that if I already have a pretty accurate nonlinear model, I am much happier with my results if I do like a Monte Carlo and run the simulation thousands of times, and I vary all of the parameters with the statistical variations that I expect and see how it's going to how it behaves, more so than doing a sensitivity analysis on a linearized model. I wouldn't have a whole lot of confidence. I wouldn't, unless I was confident how nonlinear my model was, I wouldn't have a lot of confidence that was going to produce anything that I could sort of hang my hat on. And so what I've done is a Monte Carlo approach to sensitivity to make sure that everything the system's still going to perform within some requirement or within some specification, no matter what combinations of all of these statistically likely variations, however they occur, whether they're gain in phase at the very high level, if you're just talking about gain in phase margin, or whether it's something like this sensor's angle random walk variation, and noise can swing between these two values. So let me run the simulation 1,000 times by swinging this all around, make sure I'm still good.
Yeah. That's what I do as well, is usually I'll just add in a bunch of, nonsense into the system to try to kick it in the simulation and try to see, where those margins are just experimentally. And I know from talking to other controls engineers, like in the industry, that's the approach that you said, the Monte Carlo thing. That's definitely an approach that's used a lot. Is just, we're just going to run this 1,000 times, and try to kick the system in a couple of different ways and see what comes out to make sure that even if things aren't exactly as we expect, the system will still be stable. The next one here from Chris Silva again. The system I've worked on is IMU plus 1D position sensor. So if there's any tilt in the IMU, it looks like real acceleration. That's going to be hard to align. That's like an alignment thing, I think. Anyway, Michael Gunderman has a question. So with what you said about pretending there's no gravity for using the feed-forward controller, what keeps the vehicle from losing/gaining altitude as a function of throttle versus thrust changes with the battery, because there's no I component? Michael, so I actually do have an I component in there. It's a separate I controller that I model in the nonlinear simulation. So I get all the gains from the linear sim, and then in the nonlinear simulation, I cooked up a little I controller that looks at the altitude of the vehicle over time, and then I cooked up it's just a ramp block that I use to represent it's a ramp and saturation block that I use to represent the decrease in fan speed or fan power over time as a way to represent the battery voltage dropping. And then so I set that at what I've experimentally seen the battery rates drop at. And then the I controller is just tuned to sort of compensate for that based on the altitude to give it that extra juice to get back up to altitude. So there is an I component, but it's separate, and it was all built in the nonlinear simulation, not the state space stuff.
So actually, Michael hit on a good question there, and I think the answer is you can't have a static LQR only controller assuming gravity if your thrust changes with battery voltage or something like that. For whatever reason, it's just not going to work. So that's an example where you're going to have to do something different, right? And you could wrap an integrator around it. You can have a separate integrator like Joe's doing. You could do adaptive control, or you could still do it with feed forward, right? But now your feed forward algorithm is a function of battery voltage or
the current. Yeah.
Right, so you can still attempt to cancel gravity feed forward. You just have to be a lot more smart about it, because now your system state isn't static. The envelope in which you're operating in is changing, and then that's going to change your steady state throttle position, or really your steady state like PWM or whatever it is that you're sending to outputting from your controller. And so you would just need a fancier feed forward algorithm to account for it. Or if you're not that smart, not smart in that way, but it's impossible to predict, you do something else. You put an integrator in there somehow, or adaptive control or something else.
He asked, could you also fix that with an additional set of states?
Can you fix that with an additional set of states? I mean, yeah, you can almost always do that. Like you could, you can make a state that's your nominal gravity canceling throttle position, and then you can estimate that over time. You can feed that into your Kalman filter, and then based on what you think you're doing, if you think you're doing the right thing but you're losing altitude, you can basically be just marching that thing up. It's essentially an integrator then. So that's all it is, but you're treating it slightly differently. You're treating it as like an estimated state, but I think it's going to accomplish the same thing, which is march that estimated state up just like an integrator would.
Yeah. And then the last question here, unless anyone wants to drop any more questions in the chat, did you ever happen to deal with a cascade control system and be allowed to tune only the inner loop is this an impossible task?
It is absolutely not impossible, and it's almost always the way that it's done. An example would be well, I'm going to switch to satellites because that's what I do.
Yeah.
Let's imagine a satellite, and the way that you want to rotate that satellite is with a reaction wheel. So it's just a motor with a big flywheel on the end, and so when you torque it in one direction, there's a reaction torque that moves in the opposite direction. So you can spin the wheel up in one direction, and then the satellite's going to rotate in the opposite direction. So at a very high level, the outer level, you've got some attitude control law that says, hey, I want to be pointing over at the sun. That's an outer control loop. And it says, start torquing, start adding torque into the system. Well, before you ever do that, the inner loop is the motor controller, the one that's actually saying, hey, motor, spin up to 1,000 RPM. And it's going, and it's getting all the way up there and saying, done, 1,000 RPM, right? That's the inner controller. That's the inner loop going. So you start with that typically, and you just throw away the rest of the vehicle. And you're like, man, I just need to get this motor controller working. When I tell the motor to go to 1,000 RPM, I want it to get there. And I don't want it to overshoot, and I don't want it to have so much ripple, and I want it to do all of the things that I want it to do. And once you finish tuning that inner loop, then you go out and say, great, now I know that when I command my motor, it's going to do what I want. Now, how do I command my motor to do the next layer, which is change the attitude of the vehicle to where I want to go? And, there's not a good rule of, this isn't a hard, fast rule of thumb, but typically if your inner loop is, maybe 10 times faster than your outer loop, you can pretend that it's not even there when you're tuning your outer loop.
Yeah.
So for example, I might say, go to 1,000 RPM. And if it's at 900, I know that this motor is going to get there in a fraction of a second so fast that my big sluggish satellite, my big sluggish outer loop control law is not even going to know. In which case, I can just ignore it, tune my outer loop completely separately, and then put them together and know that everything is going to be good. So in that case, that's how you would tune those two things. The reason why the drone example or cascaded PIDs for rocket control would be a little bit harder than that is because there's such tight coupling between the inner loop and the outer loop. You can't just separate those as two separate problems.
Yeah.
You can a little bit, but it's not as easy because when you go to test it, you could say, oh, just make sure that my altitude is good. Who cares about everything else? But as Joe knows, you go to test that and the whole thing is just it's wobbly and it's hard to test. So that's why for something like what he's working on, testing those inner and outer loops and all of those loops together can be more difficult because they all sort of have to work in order to have a successful test.
I will say that they're certainly all coupled, and it's a little different. It's not strictly an inner and outer loop because it's the full state feedback, just from a technically speaking standpoint. But I did do the same thing when I started doing these tests, just testing to see if the roll control works or the pitch and the yaw. When I did those, I took out all of the terms in the K matrix that affected the velocity and the position, and I just forced all those things to zero so that I was only looking at orientation, and that allowed me to understand the performance of my sort of inner loop, the orientation loop or the rate loop. And then I started, now I'm in the phase where I'm trying to control altitude and position, and so those are the outer loops, because I know that what I first tested is those inner loops, and the performance was enough where I was like, okay, now we can move to the outer loops, understanding that this amount of noise or this amount of error is going to come from those inner loops. Yeah. Anyway, if anyone has any more questions, I think we're probably near the end here, but it looks like we're done with the questions.
Yeah. Again, more people are on the Discord than me. I'm on there occasionally, but everybody who's been asking questions and answering on the Discord have been great.
Yeah.
And the discussions there have been really, really good. And occasionally I might chime in. So I would encourage people to go to Joe's Discord.
Yeah.
Yes, I guess is the Discord, because it's very valuable and really useful and a lot of fun.
Yeah. Well, anyway. Oh, here's one more. It's said that PID is error-based controller. Is there any control method that is not error-based? That would be feed forward, right? Because you're not measuring the error, I believe. I feel like
Well,
yeah. Go ahead.
I mean, I mean, it depends on how like semantic you want to be about it. Because in my diagram I showed you that the controllers are a function of the reference and the state. And at some point down the line, there has to be some kind of error or difference between them because it's trying to bring those two things together.
Or you just
right?
don't need a controller.
But was that, yeah.
Yeah.
But otherwise, you wouldn't need one versus the other, right? At some point, you're trying to look at the difference between those two, which is an error. PID uses error explicitly, right? That's the input into it, so it's very, very obvious. Whereas something like a neural network, not obvious at all, right? You're just throwing in the reference and you're throwing in the state, and somewhere in that jumbled, some of those layers maybe is error, but maybe not. It's who knows, and what comes out is controller. But at some point, it's still trying to drive those two things together, and so. But you were right. I cut you off a little bit too early, Joe. Feed forward absolutely does not use error, right? Because that's just a function of the set point. So feed forward control, not error-based control.
I see two more questions in here. The first is, hi Joe, where can I find more details about the Discord group? I came here from Brian's Patreon. Brian, that's crazy.
Oh,
we were wondering if anyone came here from there.
Yeah.
That's excellent. Well, the Discord for me is also connected through the bps.space Patreon. And so that's patreon.com/bps_space, I think. If you put it in the search bar in the platform, you'll find it. But and then Nathan has a question. Would more complex control systems make an echo landing more likely / easier to do? Nathan, absolutely. This is maybe the last question we'll do, but the reason I've stopped doing the echo vehicle for now, at least. It's not necessarily like permanently stopped, but I started writing the code that works on echo in the spring of 2017, which at this point we're coming up on like 3 years ago. And I was a much differently skilled, that's a diplomatic way of putting it, but differently skilled person at that point in terms of the code that I was able to write. So at some point, the code base was just all super messy. And I was building on a lot of stuff that just, I realized like 2 months ago, all of the calculations that I had done for really small radian values, which are, you really want a lot of points of precision for those if you're integrating a small like radians per second or something like that. But there was something where they were all like double precision, or they weren't the full precision that they should have been. And they were just, the point is with Sprite, I burned everything to the ground figuratively and started over from a clean slate, so that for going back to rockets after Sprite, something that's strictly based on a solid rocket motor or whatever, we can implement all these much better control software. We can implement that on a platform like Echo, or on a vehicle like the Falcon Heavy model, something that requires a much more complex system, especially for the Falcon Heavy, man. Just way too many staged PID controllers. It's kind of a miracle that it worked. So that's the goal with Sprite, and that's the goal. So
Joe, something that might be interesting if you ever take that back up again is you could try to land using just control, right? If I'm tilted off, make me go vertical. As I get closer to the ground, slow down, and hopefully stop right when I'm at the ground, right? You could just set all of that up.
Yeah.
Another thing that you could look into, which may or may not be more complicated, is on the planning side, right? Is you can, right when you disconnect from whatever the thing's bringing you up in the air, you could say, what's my altitude, what's my current state, and then chart a path to the ground based on your knowledge, under constraints, based on your knowledge of how much burn time I have and all of that stuff, and then build a profile, and then your controller just has to follow that profile. So it removes the complexity from the control system, but it greatly increases the complexity on the planning side of things.
Yeah.
But you may have more control over how it comes to the ground that way.
I mean, I think there's so many things that could just in obvious ways be improved with the situation, between switching to an even marginally better inertial measurement sensor to I've really been focusing a lot on splitting up my flight controllers in terms of a high rate integration for the gyroscope's computer that focuses on that doesn't get bogged down with tasks like writing to flash memory. There's a whole lot of stuff that can be improved. So yeah.
Well, I'm going to follow along and live through you, because I don't get to do any of these fun projects.
Well, anyway,
They're pretty awesome.
speaking of what you get to do, we'll end it on what you do. So if you want to follow any of Brian's work, there's a link in the description to his YouTube channel, but he does a whole lot more than that. And I believe, I can't remember what your website is. It's controls.
Yeah, I was going to say that's a better place.
Yeah.
It links both that and my MATLAB Tech Talks and some of the other stuff I do there. So it's just engineeringmediallc.com. So it's a mouthful, and it doesn't read very well when you write it all out.
Let's see if I can type this in here. llc.com. Will that work? I think I needed to put the HTTPS in there. Hold on. I'm just typing it out. Oh, I think that should work. Yeah, there it is. Great. So the link is in the chat there.
Yeah, and you can go to like more videos, which has all the MathWorks ones, and then you can go to my channel if you want to see some of my older stuff.
Mm-hmm. One of the things that I really like, if I could recommend anything that people start with, the drone control series that you did with MathWorks. I've watched that maybe 4 or 5 times now. I think it's really well done in terms of diagnosing and walking through the whole control process with one of those real-life Parrot drones. That was a great series.
Awesome, yeah, thanks.
Yeah.
Also, I haven't heard of Popov criteria. I just Googled it here. I'll look it up. But is that the university that you're at, or work at, or go to school at, or something?
Huh. Yeah, that's interesting. Well, anyway, I think that's probably going to do it for us.
Yeah.
Yeah.
Sounds good. Anyway,
yeah,
I had a
good
blast.
guest.
Hopefully this was helpful. And I'll be on and about the Discord occasionally, but you're always there. So
Yeah.
we'll see you guys there.
All right, folks. Well, have a nice evening. If anyone's interested, the Electron is launching in about 15 minutes, so they'll have a stream for that from New Zealand, I'm sure. Anyway, all right. My name's Joe Barnard. That's Brian Douglas. We'll talk to you guys soon. We're gonna go offline now. All right. See ya.